Hello, my name is Paul de la Pla, and I work at the Center for Biomedical Imaging in Switzerland and at the Biomedical Imaging Group in EPFL Lausanne, Switzerland. Most of the work on these slides is Professor Michael Lunders on the EPFL's Biomedical Imaging Group. So what we're going to talk about today is biomedical imaging or biomedical image reconstruction as an inverse problem. And to do that, we will first identify a few common elements to all image reconstruction problems in biomedical imaging. First, there's a biomedically relevant quantity S, which is usually defined over a continuum. It's a function. And then there's the representation of this function inside our computers in order to reconstruct it. Then there's our representation of the processes that allow us to image that function. It's usually instrument physics, process physics, etc. And then there is some concept of noise or statistical variability, which throughout the presentation we will assume to be additive. So the talk is composed by two chapters. First, imaging as an inverse problem, covering the basic setup I just mentioned. And then two, a condensed history of image reconstruction, where we will go through first, second, and third generation methods for image reconstruction. So several examples to show you that the setup that we're proposing makes sense for real-life applications. First, 3D wide-field microscopy, in which we have an image which depends on 3 dimensions. And there are several colors because we're observing different fluorophores at the same time. Here is an example of a C. elegans embryo, which by observing it through a microscope, basically we would get something like this, which is simply a blurred version. And we would want to recover the highly resolute version from the blurred version. Second, there's the example of ELISpot and fluorospot immunoassays, which may be a bit out there, but I think it's quite interesting. I'm very proud of it because it's part of my PhD. And it has some particularities. So for example, there's a few cells that get activated, and what we want to recover is their location and their behavior through time, as well as the proportion of cells within a sample that get activated. So you let some time incubation and you take a picture and you get something like this. And from this, you would like to recover the 3D history. So basically, it's interesting because you have a 2D observation, simply an image, and you want to recover a 3D history over space and time. So this is very timely because this method actually holds promise for analysis of vaccine development research for COVID, for example. So example 3, much more relevant to your research probably, positron emission tomography, in which we have gamma annihilation happening inside someone's brain, and we put that patient to the scanner and we obtain a cyanogram data like that, and we would like to be able to recover that, which could be 2D, 3D, 2D plus time, 3D plus time, depending on how one does the binning. So let's start. Imaging as an inverse problem, basic elements. So as our lab is in Switzerland, we're going to do comparisons all the time towards the world of clocks. So these are the basic pieces that allow us to build them. So the first piece is the unknown molecular on an anatomical map, S of R, which is a function defined over a continuum in space. And we will generally assume that it's an L2 function, so it's in the space of finite energy functions. Then there's an imaging operator that brings this infinite dimensional function into a finite dimensional vector of measurements. And this we're going to call our imaging operator. Then, because we assume that this imaging operator is linear, so if you see one thing and the other apart, you will just get the sum of the two images when you see them together, we can rely on a very heavy structural functional analysis to tell us that each of the dimensions of the measurement will be completely characterized by something we call the analysis function at M of R, which basically tells us each of the dimensions of the measurement is going to be basically composed of an inner product between this analysis function and the unknown molecular on an anatomical map that we want to find. So a word of caution here, if you want to do image reconstruction, you first have to study the physics of the problem at hand. So depending on the field that you get involved in, you may need to read any of these different books. But good news are that most imaging operators are made of a few very basic components that we're going to go through now. So first of them is the Fourier transform, because obviously, as this very randomly chosen image shows, images are made of sine waves. And what does the Fourier transform does? Well, the Fourier transform analyzes an image in terms of patterns such as the one on the right, so of complex sinusoids or complex exponentials. So basically what it does, it goes through the image and takes inner products with these complex exponentials, and this results on a number of coefficients that are called the Fourier transform. And then the result of this is that you can reverse this process by taking these weights that came out of the inner products with the image and putting them again in an inner product setting with other complex sinusoids and recover the image in this manner. So seeing is believing, and therefore what I've done now is to take the Fourier transform in a discretized way, of course, and just keep the few coefficients that are largest. So for example, this is the representation of the image if we only allow 2 sinusoids. And then at every click, I'm going to multiply by 2 the number of coefficients I'm keeping. By doing that, we see that at this point, we can already probably recognize the legs of the animal. And at this point, the sinusoids that are more characteristic in the animal's height start to appear. So slowly and slowly, we can see that the image is reconstructed by adding more and more sinusoids into the mix. And at some point, when we get to 2 to the power of 16 sinusoids, we obtain the same quality as we were having, 16 bits. So a very direct application of the Fourier transform is in magnetic resonance imaging, because actually magnetic resonance imaging was designed in order to provide measurements that agreed with the Fourier transform model. So how this is done is a gradient of magnetic field is created throughout the scanner that corresponds to a specific frequency. And then when this is done, the forward model for the magnetic resonance imaging scanner is simply the Fourier transform at a specific frequency. What this means is the equivalent analysis function of an MRI scanner at a specific frequency is simply the complex sinusoid at that frequency. This kind of modeling can be extended easily when there's coil sensitivity. So there are imperfections in the creation of the gradient, and the specific coil has a sensitivity throughout the spatial domain. So what one does is usually calibrate the machine and obtain this coil sensitivity weighting function, which just comes out as part of the analysis function, like so. Clearly, then we need one more operator as part of our toolbox, which is the multiplication operator, which just multiplies by a positive window function that is continuous and bounded. So a specific case of this multiplication operator of relevance is when you multiply by a complex sinusoid again, because in Fourier domain, this simply corresponds to a shift. Applications of the multiplication operator, as we've seen, are to MRI with coil sensitivity, but also to structural illumination microscopy, in which you keep changing the illumination pattern under which you image some sample in order to, over the accumulation of different illumination patterns, get rid of the diffraction limit. A similar operator is convolution. Convolution is also characterized by a simple function over the spatial domain, which is called its point spread function or impulse response. In convolution, you simply average local values of the signal using this kernel impulse response or point spread function, which actually comes out to be the analysis function. So the analysis function of a specific sample of a convolved image will be simply the kernel or point spread function of that convolution at that point. So a specifically relevant characteristic of convolution is that if you take the frequency response of the convolutional operator, so simply the Fourier transform of that PSF, the convolution is simply a frequency domain product, meaning that you can implement a convolution by Fourier transforming, multiplying by h hat, and inverse Fourier transform. An example of application of convolution is 3D wide field microscopy, in which you have illumination light, which is processed in order to illuminate the sample as evenly as possible. But the fluorescence that comes back from the image does not come in a planar wave, and therefore the rays that come from a specific point have traversed several points, and the behavior or the components of the image that you get at each point are blurred. So there's an effect of a 3D convolutional kernel such like this one that smudges the whole image. Another operator that clearly is very important for tomography, be it positron emission tomography or computerized tomography, is the Radon transform. The Radon transform has the particularity that it cannot be defined directly over the space of finite dimensional finite energy functions, but instead we have to go to some more generic mathematical space that restricts a bit more the continuity in order for line integrals of a function to be defined. Basically, the Radon transform takes a specific direction theta perpendicular and simply integrates the image throughout that direction. So by doing that in different directions and obtaining these profiles of these line integrals depending on the shift, if we do that with a node of rotations, we have a complete characterization of the image equivalent to having it in the spatial domain. So this can be expressed again in terms of an analysis function, in which this case it's not actually a function, it's a generalized function, in the same manner that the space that we usually chose was the space of finite energy functions, and now we had to choose the Schwartz, the space of Schwartz functions. But anyway, with this analysis function, the integral over the spatial domain comes out to be the line integral we're interested in. Data of tomography data that follows this model look like this. So you get this in the spatial domain, and this would be the equivalent sinogram. So the image that depends on the angle theta and the shift t that we've chosen. The Radon transform has a relation to the Fourier transform through the central slice theorem. So basically this theorem says that if you take the Fourier transform of the image and you look at a specific line on a specific angle, this will result in the same function than doing the Radon transform with the same angle of the image, and then Fourier transforming the result of the Radon transform. Here it's stated. So if you take the Radon transform and then do the one-dimensional Fourier transform, this is equivalent of taking the two-dimensional Fourier transform of the image and looking at a specific direction. So what we have learned now is that imaging operators are simply characterized by analysis functions, and that these analysis functions, with a few of them, we can characterize many popular modalities. 2D or 3D tomography, we go for the Dirac pulses in the direction that force the direction of the line. 3D deconvolution microscopy, we have simply the PSF of the microscope. Structural illumination microscopy, we have the PSF of the microscope multiplied by the illumination pattern. In positron emission tomography, again, we have the Dirac pulse like in computerized tomography, but here the theta m and tm mark the mth line of response instead of being the ones that we decided while scanning. In MRI, it's simply the complex exponential or complex sinusoid, while in cardiac MRI, where you would usually use a parallel MRI setup in which different coils have different sensitivity, you can incorporate the weighting function for each coil. So now that we know how to compute the measurements from the function, how do we represent this function which we ultimately want to recover inside our computer? For that, we use usually a finite dimensional basis or a finite dimensional set of synthesis functions shifted across the domain. And in that manner, we can represent our continuous function here with a few coefficients s, so with a vector of coefficients of dimension k. So an example here is we are representing the piecewise linear approximation of a parabola in terms of a sum of triangles with different heights. Applying the forward imaging operator to any of these signals that we represent with a few coefficients and synthesis functions, it's easy because it turns out that in the end, we only need to know the inner products between the synthesis function and the analysis functions. So that turns out to be equivalent to formulating a discretized problem such as that, where H is simply composed of these inner products. What properties and examples of basis functions and properties that we would like them to have are, for example, the shift invariant representation, which we generally want because we want to have the same approximation properties throughout the spatial domain. We would like a separable generator because we would like to be able to design separable algorithms for many of our image reconstruction chores. So for that, we need a separable representation of the signal too. The most common here is the pixelated model, in which we simply assume that the signal that we're trying to recover is piecewise constant. That's equivalent to using splines of order 0. Then the next is to use triangles, which are equivalent to using splines of order 1, and basically assume that our signal is piecewise linear. And then there's in the other extreme, there's the band limited representation, in which our synthesis function is a sinc function. And this is sort of an equivalent of taking splines to order infinity. So now for a condensed history of image reconstruction. It is condensed because of time limitations, and therefore I'd like to point you to a long ICAST tutorial which we gave back this year, which covers it in much more detail. So first generation methods for image reconstruction, they start off from the assumption that our problem is well posed. What does that mean? Well, this condition here basically is saying that we don't have an null space to be spoken of in the operator H. So that means that the norm is sort of equivalent in the space that H brings you to the original space of the signal. So this would be sort of an equivalent of saying, okay, just invert the matrix H. An equivalent that has often been used is back projection, in which you substitute the inverse by the transpose of the matrix. This has the advantage that it's a very simple strategy to bring the measurements into the space of the signal, of the image, but it's only the equivalent of the inverse if the transform is unitary, which is in a very few cases. A similar approach or a similar thought process, a bit more formalized, is okay, I'm just gonna wanna find the signal that when passed through my imaging operator is closest to the measurement. That is what is known as least squares because one uses the L2 norm. So this implies this closed form solution, which is simply a generalized inverse to the left of H. Limitations of these approaches are that they amplify the noise. They, of course, most interesting problems are ill-posed, so the condition is not given to start with. And then that inverting matrices this large is computationally expensive. Just think that the matrix H has as dimensions the number of pixels in your image or the number of synthesis functions that you use to represent the image times the number of measurements. Generalizing it a bit more is using Tikhonov-Wiener theory, in which we solve this optimization problem. So this came initially, Tikhonov proposed something like this. Let's use an L, a transformation of the signal, and penalize it. And we should choose the transformation in a manner that the overall strategy promotes smoothness. So that would mean, for example, choosing L as the gradient and therefore penalizing the gradient of the signal, and thus incentivizing the signal to be as smooth as possible. An alternative approach is that of Norbert-Wiener, which simply said S is a normal multivariate vector with mean 0 and a specific covariance matrix. And it turns out that at least throughout the maximum a posteriori formulation, both problems lead to the same optimization. Both setups lead to the same optimization problem, in which L simply corresponds to the square root of the inverse of the covariance matrix. So the closed form solution of a Tikhonov minimization problem is this one here. And this can be interpreted as a filtered back projection, in which you simply take the back projection and then process it here by something we could call filtering. Indeed, in most efficient implementations or in most problems, this will turn out to be a convolution operator, and that can be interpreted as a filtered back projection. Limitations of these approaches are, yet again, that if we were to implement them in this manner, matrix inversions are computationally expensive. Therefore, we need efficient iterative algorithms that solve this problem. In particular, because we're doing image processing and the size of the variable is really, really large, one would usually recur to steepest descent type algorithms. For example, the projected gradient descent, which simply does a gradient descent step and then projects to the non-negative part by simply putting to zero those coefficients that have turned out to be negative after the gradient step. If we look at the structure of the main element in the least squares term, we see that it's easy to derive the derivative of this term with respect to s, as the steepest descent algorithm requires. It will be simply 2 times HTY and then 2 times HTHS. Indeed, if we change the definition of the step gamma for our presentation to look better, the least squares algorithm will simply say, okay, you take the point where you're at, and then you try to bring your signal when it passes through the operator and then it back projects, be as similar as possible to the back projection of the measurement. If we do that in this simple case in which we're trying to recover from Gaussian blur and additive noise, we see that, as we said before, the simple problem that this approach has is amplification of the noise. So while first it recovers a better quality image of this cat, it slowly starts degrading when the role of the noise becomes apparent. If we instead go and take the Tikhonov problem instead, it's easy to see that this simply adds this term LTL here inside the operator that is applied to S at every iteration. This, in a way, usually guarantees that for a specific regularization parameter lambda, we always will end up with the same image. But here, of course, there's the choice of lambda, which regulates the compromise between smoothing the image too much and letting the effect of the noise in too much. In this example, for example, we see that with lambda 0.2, here the noise is still apparent. With lambda equal 2, it seems to be an ideal compromise because with lambda equal to 20, we have an image that is way too smooth. So fast implementations of these algorithms are usually related to FFT-based implementations. So for that, we need convolution matrices. So we need that these multiplications by matrices here are equivalent to a discrete convolution. This is applicable to, for example, the convolution microscopy or the original formulation of the Wiener filter, because if H is a convolution matrix, so it will be H transpose H. Then it's also applicable to parallel ray computed tomography, so in the end, filter back projection, because HTH is a convolution matrix. And then also to MRI, because the H matrix in MRI is simply based on Fourier transform coefficients. For sparsity-based reconstruction, the whole story starts from the idea of breaking out of quadratic regularization. So in classical methods, we had quadratic regularization. The concept comes to just use other p's, so other norms for the term ls, and it particularizes in norm 1, which is known to generate sparsity, as we will tell you now. So the first approach, or the most known, is that of total variation, in which you choose L as the gradient, as we had discussed before, but you simply change to the 1 norm. More developed approach come from the concept of sparsifying transforms. So this graph is a parallel to the image of the zebra that we saw before, in which we dropped coefficients and then tried to recover the image anyway, and basically shows the normalized mean square error as a function of the percentage of coefficients that you keep in logarithmic scale. So basically what the graph shows is that there are transforms, for example, the discrete wavelet transform 9/7, which retain much more information in few coefficients than Fourier did. By relying on those transforms, then we can design more principled regularization schemes in which we say, if natural images are sparsified by these transforms, that means that we should be looking for a signal that can be expressed with respect to this transform with a sparse vector. And then we penalize the one norm of this vector that we want to be sparse. A formalization of this setup comes with compressed sensing, in which we assume precisely that. We assume that we have a vector of dimension n, which is sparse. So basically the number of non-zero coefficients is much smaller than the dimension. And then we merge the effect of the sparse representation and the imaging operator into a matrix A. And we assume we're in the undersampled regime. So we have many less measurements than the dimension of the X we're trying to find. So these assumptions are combined in this drawing I'm sure you've seen before, in which you see that we have a fat matrix, a long vector with a few non-zero coefficients, and so on. So the result that is more relevant to compressed sensing is simply that we can solve a convex problem, which is simply constraining the L1 norm to be somewhere and then trying to find the signal that is closer to the measurements. And that will be actually equivalent to finding within the set of sparse vectors the signal that is closest to the measurement, with some conditions on A, of course. I'm glad to say that this theory was pushed forward at our group, in which a representative theorem view of the subject was developed. So here, the regularized setup of the optimization problems, which is much more close to our setup in inverse problems, was shown to be equivalent to this minimization of the balls subject to a constraint on the how far the simulated measurement, so X passed through A, was to the actual measurement. So this constraint here can be visualized in this one-dimensional example in which A is simply a vector as this band C where AX should be. And then what this illustration shows, and this illustration is quite common, is that by using the L2 norm, we choose a point that is not sparse, but by using the L1 norm, we choose a point that is sparse. A generalization of this that is commonly not seen is that if the matrix A does not fulfill the conditions of the compressed sensing theory, this other situation arises in which still the minimization with the L2 ball gives a non-sparse vector, but if you minimize using the L1 norm, then you have a non-unique set of solutions. But the important thing is that you have sparse extreme points in this set of solutions, and therefore you can still find a sparse vector that has a good explanation for your data. So the formalization of the theorem goes like so. If we're trying to minimize the L1 norm within a constraint on the imaging operator lying in a closed convex set, the theorem says that the set of results will be convex, weak star compact, and will have extreme points that are basically sparse. So another view parallel to that of Wiener and Tikhonov in classical reconstruction methods, the corresponding statistical view for these sparsity-based reconstruction methods is that of sparse stochastic processes. In sparse stochastic processes, we assume that there is an operator L that whitens our continuous signal. Then we discretize the problem and we say, okay, that is equivalent to saying that U, a transformed version of the signal, equals LS, with L a discretization of the whitening operator, and the distribution of U is infinitely divisible. Approximately, this is equivalent to the maximum posteriori formulation, such as that, which basically comes out to be the same problem as that up here, but a bit generalized because here the distribution of U can be chosen differently. So in specific, if we choose U to be Laplace, this will be equivalent to the one norm. But this setup gives us the option to choose other options for U, which also induce sparsity and are different than the Laplace model. This whole field is supported, the field of the second generation reconstruction methods is supported by proximal optimization algorithms, which are the workhorse inside. So we will focus on an example, which is the alternating direction method of multipliers, basically because it's a one tool fits all setup, which may not always be the most efficient, but it's generally easy to implement and adaptable to different problems. So for that, what we do is we extend the optimization problem by creating a dummy variable U, which equals LS. And then we set up the same optimization problem, and we will exploit the separability that the creation of this dummy variable gives us. So to do that, we first formulate the augmented Lagrange, which basically has the cost function here, a Lagrange multiplier, and then a penalization term for not fulfilling the constraint. The ADMM algorithm is separated in these three steps, in which the first one is a linear inverse problem. So it's the equivalent of solving a Tikhonov regularized problem in first generation. And the second updates the Lagrange multipliers, while the third takes care of the regularization. And it's in the form of a proximal operator, which is another minimization problem that usually has a pointwise solution. So the nice thing about this is that we can decouple the effect of the linear step, so solving a linear inverse problem that is specific to the imaging operator you're using from the statistical step or the prior step in which you're designing a denoiser that denoises the data according to your statistical knowledge. A particular example to see the relation with denoising is that of choosing L to be a wavelet transform and choosing the regularizer to be the one norm, because basically that turns out to be the wavelet thresholding denoiser. So basically you would, this proximal operator has a closed form solution for the L1 norm that looks like this. So basically it takes all values between minus lambda and puts them to 0, and values outside there are simply pulled towards the middle by subtracting or adding lambda where relevant. So this, in the end, if you do it with the wavelet transform, this will simply take small wavelet values and put them to 0 and just shift the other ones, which is a very well-known denoiser that is quite fast to implement. Advantages of second generation image reconstruction methods are the higher reconstruction quality, that they're amenable to low dose, faster imaging, so less time for patients inside the scanner and lower radiation doses through the compressed sensing setup. And then that we can reuse the fast implementations of first generation methods in the linear inverse problem inside the ADMM approach. The limitations and of course an increased complexity because each iteration includes a linear inverse problem, and that they are challenging to implement efficiently because they rely on this huge setup of efficient first generation methods, efficient implementation of these complicated proximal optimization algorithms. That is why we have a MATLAB library, GlobalBioIm, where we provide many of the implementations in order to ease up everyone's research. So you have more details in the links. So now we go into the third generation methods. And the overarching topic is here, how do we leverage what we already know? Because when we talk about third generation methods, what we're basically doing is taking over-parameterized models that are being used for anything from image classification to driving cars nowadays, and we're using them to reconstruct images. So a risk with this is to forget about everything we know from the previous generations of algorithms. So here I've tried to draw a line that separates things by the dimensionality of what we're trying to learn. So in classical and sparsity-based reconstruction, we may want to learn the lambda, so the regularization parameter, or we want to calibrate our forward model for parameters that we're not able to measure. Going a bit more to the right, we could have dictionary learning. So we could say, like, we don't know which is the best sparsifying transform for this problem. So I'm gonna learn that from the data. We could, and typically here you wouldn't be using still neural network setups, but you would still be able to formulate statistically or in an optimization framework how to find this optimal transform. Going forward, you could say, okay, no, I'm going to use the second generation methods, but the nonlinear functions like the regularizer, I'm going to learn through this setup of deep neural networks or convolutional neural networks, which are the neural networks that make sense in imaging because basically convolutional structures appear everywhere. And then you can go farther, but still within reason, and say, okay, no, there are specific tasks in image reconstruction that I want the convolutional neural network to learn to do. So it could be artifact removal for first generation reconstruction. So you could have a very fast first generation reconstruction and then try to teach a convolutional neural network how to map that very rough reconstruction to a high quality image. Of course, for that, you will need an extensive data set of very good reconstructions in order to teach the convolutional neural network how to do that mapping. Indeed, that was the approach taken in Jin et al. 2016, which we're proud to say in the group that it got the 2019 Best Paper Award by the IEEE Signal Processing Society. Then there's also the concept of doing super resolution in 3D imaging, where you're imaging isotropic objects. So you may have in 3D imaging, it's common that there is one of the directions in which your resolution is much worse than in the others. So you can harness how objects look in the other two dimensions in order to recover resolution in the dimension where it's harder. Then there's the setup of speeding up while performing second generation methods and simply putting some components of learning within them in order to speed up things. And then, of course, there's the other case in which you have a well-performing reconstruction method that works with high dose setups or long scans with lots of data, and you get something that works well with low dose. So you basically artificially reduce the dose in the extensive data that you have and try to map a neural network that from the reconstruction you get from the low dose regime to that of the high dose regime. But of course, well, first let me show you the kind of results that these can provide. So while here we have a ground truth computerized tomography data, a first generation method reconstruction, a second generation method reconstruction, and a third generation method reconstruction, particularly that of the paper that won the Best Paper Award. And here we can see that between first generation and second generation, which supposes a substantial increase in computational performance, we get a 5 dB difference in SNR. But the important thing here is that from second generation to third generation, we also get a 5 dB difference. And actually, at least at reconstruction time, the computational complexity of the third generation method is not much more or even equal to that of the second generation. However, there are also the risks of going too far to the right, like the world has been having lately. So ignoring the physics and learning them instead is not a good idea. There's a paper in Nature, which is quite well known. It's called AutoMap, and it intends to learn image reconstruction for any problem independently of the physics. So the guiding principles that we recommend for using convolutional neural networks and deep learning for image reconstruction are to learn image-to-image maps. So you either stay within the image domain, sparsified or not, or you stayed within the measurement domain, but you don't cross the boundary that is usually provided by the imaging operator, which basically should be at least based on the physics. Then, of course, for developing this kind of algorithms, you need very large training data sets with gold standard reconstructions to know what to train towards. But don't be challenged by that, because depending on the problem structure, these databases may not need to be as large as you may think, depending on the inner structure. Then there's the fact that you should augment your data. So the models typically do not know what are the relevant properties in your problem, and therefore you need to modify the data so that the model has seen all possible combinations that you would consider equal. My favorite strategy for developing deep neural network architectures is that of unrolling, which is based on a paper by Gregor and LeCun in 2010. So there you basically use second generation methods as a starting point for a deep neural network, which motivates the architecture using optimization. In fact, what you do is you have here is an example from my own research addressing the problem of the immunoassays, which is basically inverse diffusion. So here we see FISTA, which is a specific second generation method in which we see here H, the transform, H transposed, we have here a proximal operator, etc., etc., etc. What we did then was to simply have this structure, but learn some of the parameters. And here it's very comfortable to combine which parameters you learn and which you don't with these options that we've presented before. Anyway, a word of warning on the use of convolutional neural networks and deep neural networks for image reconstruction. Here is a paper in PNAS of this year on instabilities of deep learning in image reconstruction. So here you can see an example of an image where some very small perturbations have been added, which are almost imperceptible to the eye. Then what happens if you try to reconstruct that image using state-of-the-art algorithms? Well, basically the differences are also almost irrelevant to the eye. But what happens if you try to do the same thing with a convolutional neural network that has been trained only on clean images? Well, this happens. You completely destroy the reconstruction. And here, this is the authors propose that this is due to something called kernel or null space awareness, in which while second generation methods used to always know very well the kernel or null space of your imaging operator, deep neural networks don't. And basically, the authors have theorems in which they can prove that for wherever you do, basically they can find an example that creates these effects. So finally, some references. The most important one, the tutorial on biomedical image reconstruction from the Foundations of Deep Neural Networks, which basically presents the same storyline as here, but with many more details. Then the book on sparse stochastic processes, and a couple of papers on the theoretical characterization of compressed sensing or L1 regularization. Then there's the manual to our, or a paper manual to our GlobalBioIm library, and a bunch of applications, including those of the immunoassays I discussed at the beginning. And then some papers on neural networks applied to image reconstruction, including the one that won the prize for the IEEE Signal Processing Best Paper Award. So many thanks to the current and former members of the EPFL's Biomedical Imaging Group, but overall to Professor Michael Runzers, whose vision I've been trying to present in this presentation. And of course, any credit goes to him and any error is probably mine. Thank you very much for your attention. Goodbye.